Next section introducing our next presenter, Riccardo Felici. Riccardo has experience of project managing and lead offshore engineer in numerous offshore renewable projects in the Asia Pacific and emerging markets. He has over 6 years specific experience in the installation of offshore wind farms and large submarine power interconnectors. He's now leading the OWC Vietnam office, where he's managing a variety of renewable energy projects, including nearshore and offshore wind farms. Thank you.
Thank you, Faraz. Could I share a screen, or is it, will you share the presentation like was done by Joe?
Is the share button available?
Yeah, I'm attempting to share. Let's see what happens. Can you see? Can everybody see my screen, right?
Yeah, perfect.
Right. So thanks a lot, Faraz, for the introduction, and thanks for the organizer for the event and giving us the chance and opportunity to speak. As mentioned by Faraz, I am the OWC country manager for Vietnam, and I have a background in both installation of cables, internet connectors, and export power cables, but also on vessel design, and as well as interconnector planning and feasibility study, the early stages of development. Today's presentation, I just want to introduce to you a bit about the OWC, Offshore Wind Consultants, and what we do typically in a project, as well as what our parent group does. And then I'll dive into a bit more of the, let's say, the details of the actual connection of a wind farm to the shore. So Drew kind of gave a more broad overview of the grid, and we're going to look at a bit more some parts of that that grid connection, which is from the wind farm to the shore. In terms of ABL Group, for those of you that don't know us, we are a leading independent energy consultancy, and we are committed to 50% revenues from renewable energy. And I think we're a good way there. We worked on several hundred projects, like I will show in a minute. Offshore Wind Consultants, we are we call ourselves the Offshore Wind Consultants. We have a lot of experience in offshore wind. Just within our own company, we have about 82 wind projects from 2011, and have accumulated over 68 gigawatts of experience. And this comes from technical advisory, engineering consulting, from the really early stages of development, the moment the developer tells us we're thinking of a wind farm, to actually supporting all the way through FID and actually the installation of said wind farm, including all the cable, substation and export cables for that. We have over 180 offshore wind experts globally, over 8 different countries as OWC, and we have teams in the major hubs for renewable energy, both in Europe and Asia Pacific. Globally, as a group, as I said, we're based all over the globe with over 920 employees, and we're present in 38 countries. But more specifically, we're present in the major Asia Pacific hubs, where we have main renewable offices with expertise specific to each country, but also regional expertise in terms of grid, in terms of interconnections and renewable energy as a whole. If we had to summarize our offshore wind experience specifically, there would be over 233 projects as a group, and this accumulates over 118 gigawatts. Works all over the globe, but also all over Asia Pacific, more so in emerging markets, which I think is critical in some of the discussions that we may be having later on. We've also worked with different turbine sizes from 1.5 megawatts all the way up to the latest in development, being the 20 concept designs. So in terms of today's presentation, I really want to focus more on the export cables, and I'll touch upon a bit about the inter-array cables as well, and the way we export essentially the power from the turbines to the shore. If we had to think of an oversimplification of a wind farm, we could say that of course we have a wind resource, we have turbines, and therefore turbines produce electricity, so we get electricity on the other end. But of course, this is an oversimplification, and most of you are aware there's several different factors. And today we'll focus on one of the factors, which is exporting that power from an initial point A, where the wind resources are, to a point B, where the demand actually is. If I just take the example of Vietnam, which I'm familiar with, we of course have a population density quite near the Ho Chi Minh City area in the south of Vietnam. But if we look at the resources, actually the best resources are further north than that. And therefore we'll have to connect a resource density with the population or industrial density, which is the consumption point, shown here with the black rectangle and blue rectangle respectively. So this is to say we work in a natural environment, things are not always as we would like them to be, they're not always close, resource doesn't match demand. It's also true at a regional level, and I think Drew touched upon that, where we have different resources in different areas. In this moment, we're focusing on offshore wind. So I've taken again the example of Vietnam, and if I look at the overall region, some of the areas where we know there's a high consumption rate could be Singapore, and we can see that of course there's a mismatch in that. And overall here in green, you can see the lower wind speeds, and purple the higher wind speeds, more suitable for offshore wind, I should say. And you can see there's a large mismatch as around Singapore. There's really poor wind velocities, whereas there's good wind velocities in Vietnam. So how do we get from one point to the next point in terms of distribution of this electricity? So for those of you who may not be too familiar with offshore wind farms, although I'm sure pretty much everybody knows this over and well. Of course, we have wind turbine generators, WTGs, which are producing generally AC, medium voltage electricity, alternate current. These are connected in different groupings to a substation. Depending on the distance to shore, the substation could be onshore, could be offshore. Said substation then can perform different roles, exactly dependent on this distance to the shore. Whereas we see that essentially the actual current, depending on the distance, will have higher losses if transmitted through alternate current rather than direct current, and therefore over distances of probably about 50-60 kilometers, we can see that the direct current starts to become the main advantageous current to transmit the power from, and therefore this will be used for the transmitting that power to the shore. But once it's onshore, of course, so then needs to be tied into a grid connection point. In this case, would be the main grid point to transmit that power to your demand center. If we look at a bit more closely at the turbines, the initial layouts are of course designed to optimize the wake reduction. Wake losses reduction. So they are optimized based on the prevailing wind direction, but they're not optimized such to transmit the electricity. Of course, we want to optimize our resource extraction rather than our output at this stage. But this leads us typically with the picture you see on the top left, which is quite a diverse field with different turbines in different positions. And what we need to try and do is to connect those to a single point such that we can move from that single point to the shore. This can be done several different ways. It could be typically summarized as three main connections: a star connection, which is typically seen only on really small power plants, which single cable goes from a substation to a turbine. Whereas it's more typical would be a radial type connection, whereas different turbines are connected in string, as you can be seen on the right A picture. And different turbines are connected in series to then the substation. Of course, the more turbines are connected, you can imagine that the power requirements for that cable are going to be higher, and they need to transmit more power to that turbine. And then another connection, which is typically seen, is the ring connection, which is an alternate version of the radial, where connections are then close the loop between the turbines, and those are diverted back to the substation. First, we have a ring connection, which is more reliable and can still provide offloading of power, even in case of losses of cables. Now, When it comes to the early designs, the way we would typically look at this, it's through what we call an optioneering stage, whereas different options are being analyzed, and each options will have a pro and a con. Typically be seen in differences in CapEx, so capital expenditure, and OpEx, operational expenditure. You can imagine that a ring infrastructure can offer you many more benefits in terms of operational expenditure, as one damage, it doesn't result in the complete failure of a whole string, but of course it will come at a higher cost at the beginning because we'll have to install more cable. So at this stage, typically we will look at a cost-benefit analysis and look at let's say we need to understand what are the costs involved and where are they located, if it's earlier on, later on, and what will be the benefit of different cable specifications. But let's say the key option, the key point is to have different options at this stage and be able to choose this at a later stage, because typically at the really early beginning phases, there's still uncertainty in terms of the actual turbine generators. The more critical part, and I say that the main focus of this presentation, will then come once we move from the substation to the shore. Now, as you can imagine, we just have 2 points, and I think most of us would then automatically think, okay, just the straightest line, it's probably the best. Although this is actually not often the case, there are different constraints that need to be considered. Partly geotechnical, geophysical, but also anthropogenic, so different fisheries or military areas. And these play a role into the classification of different routes. So we would typically look at several different routes with several different offloading points. Of course, we need to consider different grid connection points. And this is also to give us redundancy at the design stage, such that if one area is not suitable further down the line, we can still consider the other option. What we need to do at this stage is also identify different risks, and this could be also different stakeholders and different other infrastructure that is present in the site. Could be pipelines, could be other interconnectors, and it could be different infrastructure that then ultimately impacts on the feasibility of some of these routes. The considerations need to be made at early stage in terms of the actual routing and look based on topography, but then this has a direct impact on the cable specification. So there needs to be a feedback loop, and we know that, as I mentioned, further distances will require different currents to minimize the losses. So we could see that at distances, at large distances, we'll see a direct currents being utilized versus alternate current, and this difference will have a direct impact on the cable specification. Of course, you can imagine there's completely different cable packages themselves with different number of cables, which then lead to different corridor specifications, which are then used to define the actual route of the cable. Once the corridor is being defined, we'll then need to start shortlisting each of these routes and understanding which is more feasible and which is less feasible, and potentially exclude some of the routes from the early get-going. To do so, we consider different constraints. These would be typically natural and anthropological. The natural constraints, we look at geology and seabed morphology, and I should say also water depth, which is quite critical, especially some of the long interconnectors. For example, we're working in a very large interconnector from Australia to Singapore, with water depths in cases above 2,000 meters. So of course, this is a main design constraint, a main criteria. And we'd also then need to look at the anthropological side of things. So that is fishing activities, shipping lanes, and other, it could be military activities or other human activities that impact the actual cable route. Once these constraints have been considered and assessed, and provided the initial shortlisting of the routes, typically this information is then fed through the design stages into what's called a cable barrier risk assessment, which actually looks at the a probability risk assessment of each of these risks, including the stakeholder liaison, to ultimately define the barrier recommendation for the cable. So that is, what do we need to do such to protect this cable? Is this cable even able to be protected from the get-go? In terms of for each of this route, we will also need to assess a landfall. So for every cable, of course, at the macro level, there's a single landing point, but of course, each of this area has different approaches of the cable itself, and this may not be so obvious as it can be from initial look at the surface of this. In fact, there's different limiting criteria, but ultimately, let's say we can look at on a more practical level at the actual installation of this cable at the landfall. So this could be done typically either by horizontal directional drilling, HDD, or open cut trenching. Each of these technologies is suitable for a different type of soil and the different characteristics of that landfall. So what will happen is that we'll have to shortlist again different types of landfalls, looking at both the technology and the need on how to get the interconnector to the shore, but also looking at other geophysical, geotechnical problematics that could happen around the water, around some of the water depths near the shore point. Ultimately, as I said, similarly to what we've done for the cable route, we'll have to shortlist these different landfalls and potentially eliminate some of these to connect to be able to connect that power from the offshore substation to the onshore substation. The last point I want to touch on is in regards to the actual installation assessment. So once we have an understanding of how do we need to protect this cable, then we need to look at which tool can actually allow us to protect that cable and in which way. And this is typically done through what's called the burial assessment study, which is carried out exactly to define the type of tool. For example, at top right here is a trench, is a ROV trench. But also further to that, it's also critical to understand the vessel that will be used for such operations and understand the main limitations, such as draft, operational backdeck layout, positioning system, burial equipment, and carousel capacity. We can go in depth into each one of these criteria and the impact they have on the shore pull-in or also the inter-array cables installation. However, what I want to say, I think, is that these are critical areas that need to be considered and that will have an impact on the overall project. In terms of conclusions, I should say then that if we look at power export in an oversimplified way, we now consider that if we have wind and we have wind turbines, then of course we then need to think about where is our demand center, where do we connect to that grid, and further to that we need to consider the optioneering, so for the inter-array cables, how do we connect the turbines, and further, how do we connect that substation then to the shore, looking at different cable route optioneering, ultimately landfall assessments and installation assessments before we can get power to the house with a light bulb on. And to this extent, OWC can help on several different areas, but our primary focus would be on the initial stages of the project. So actually scoping the idea, looking at the interconnection agreements and liaising with different stakeholders onto how to optimize those agreements, and then looking at the actual cable routing, cable specifications, and cost-benefit analysis of the different options, such to be able to reach a financial investment decision together with the developer to make the project a reality. So thanks for your attention. If you have any questions, I'm sure we have a good time now to discuss.